Next up, we have Anima Anandkumar. Anima is a Brain Professor at Caltech and Director of ML Research at NVIDIA. She was previously a Principal Scientist at Amazon Web Services. She has received several honors, such as Alfred P. Sloan Fellowship, NSF Career Award, Young Investigator Award from DoD, and faculty fellowships from Microsoft, Google, Facebook, and Adobe. She's a part of the World Economic Forum's expert network. She is passionate about designing principled AI algorithms and applying them in interdisciplinary applications. Her research focus is on unsupervised AI, optimization, and tensor methods. And now, over to Anima.
Welcome to my talk on AI for Science, how we are heralding new breakthroughs through artificial intelligence. I'm Anima Anandkumar. So today, we have the promise of AI being able to deliver even 1 million times speed up in many areas of scientific computing. And this is really essential. If you think about some of the world's most pressing challenges today, one of them is dealing with climate change. And to do that, we first need to be able to accurately predict how the climate is going to change over the next decades. And that requires being able to accurately incorporate fine-scale features, information about how clouds form and how they evolve, such as what you're seeing here on the left. And being able to do that well requires about 100 billion times more computing than what we have today, according to my colleague here at Caltech, Tapio Schneider. Similarly, when it comes to understanding the properties of materials and drugs, we need to be able to go all the way down to quantum chemistry, being able to understand the interaction between atoms in their electronic structure. And doing so requires enormous amount of computing if you try to do that brute force. For instance, trying to understand this interaction among just 100 electrons requires more than the age of the universe on current supercomputers if we did this brute force. And so that's the premise for using AI in these scientific applications. We need to go beyond just standard numerical computations. We need to be able to learn better features and better transformations that can lead to accelerated computing. And machine learning sits on top of already accelerated computing with the use of GPUs, given that the Moore's law is dead, given the plateau in single-threaded computing. We need the power of GPUs and the acceleration from it. And at the same time, we need supercomputing, especially hybrid AI and HPC supercomputing that can help us scale up and out on these very challenging problems. But that's not enough by themselves. You need machine learning as a cherry on top. You need to be able to use machine learning to learn better features, be able to exploit data in many regimes and scenarios, and at the same time make new discoveries. So let me show you an example of what we've been doing in using AI for scientific domains. To begin with, let me show you our ForecastNet, which is a Fourier-based model for weather forecasting. And you can see here in this visualization that is done on Omniverse, which is the NVIDIA's platform for visualization. What you see here is between the ground truth overlaid with our model prediction here in orange, you can see really good abilities to forecast. And what here it's being visualized is the atmospheric rivers, thousands of kilometers wide. And it's really important in terms of being able to predict precipitation in the California coast where we are currently present. And it's really important to be able to understand what are drought-like conditions, the chance of fires. And so our model is able to do this accurately, and at the same time is about 45,000 times faster than current numerical weather models. We can also see the same AI-based weather forecasting model also being able to predict extreme weather events such as hurricanes. So this visualization here you see is looking at how our model is able to predict the wind speeds, the high wind speed conditions, and in particular, the trajectory of Hurricane Matthew. That was not part of the training set, and yet it's able to accurately capture these trajectories. And so it's able to do accurate weather forecasting while at the same time being much faster, about 45,000 times faster. And so with that speed means we can also do very fast ensembling. So you can have now huge number of ensembles as opposed to standard numerical weather models that are limited by the number of ensembles they have. The other is real-time interactivity. So being able to visualize and interact real time because you have inference being in a matter of few seconds as opposed to standard numerical weather models that can take many hours. And so you see here the latest visualization on Omniverse, being able to visualize, again, hurricane conditions. And in pink is the uncertainty around it. So we can enable these kinds of real-time interactive visualization. And with this help weather and climate scientists make sense of the predictions as well as intervene and look at different scenarios and be able to understand and visualize them. So to give you an overview of what we did with ForecastNet, we trained it on a large amount of historical weather data. And that's an advantage here. We have lots of historical weather data, but the current numerical weather models hardly make use of them. So they're only used to calibrate a few variables. And so we are not able to fully exploit the weather data available. Whereas our AI-based weather models are fully data-driven and can exploit them well. So that's also the reason for speed up is our ability to learn better features with data-driven models. And the one aspect of, okay, we did this AI-based model, but how is this different and better than previous AI-based attempts at weather forecasting? We are about 8 times higher spatial resolution in our forecasting. And along with it comes the benefit that we can predict to much longer timescales, up to a week or even longer, which previous AI-based models were unable to do so. And that's because we are able to capture fine scale information. I'll tell you in a bit what our AI-based model is using to do that. But the benefit from that is the ability to do unparalleled accuracy of challenging variables such as precipitation and surface winds, while at the same time being much faster. And so that's the benefits we are seeing with ForecastNet. We're also seeing advantages in a number of other scientific domains, for instance, in carbon capture and storage. So in order to have climate change mitigation, the idea is one day we need negative emissions, meaning we need to remove carbon dioxide emissions as they're being produced or even directly from air. And ultimately, they need to be stored underground in reservoir. And to model this, we need a multi-phase flow system that captures how carbon dioxide interacts with water underground and what is this pressure buildup. In order to safely store it, we need to be able to accurately measure this pressure buildup. And we see that here over a course of time, as long as 30 years, how does this gas saturate and pressure buildup? And you can see a standard convolutional neural network blurs it out as opposed to our model that has much sharper and accurate predictions. we recently also have the ability to do 4-dimensional predictions of carbon capture and storage over multiple wells. So it's not just now one well, but multiple wells, and understanding the interactions there. And by doing it as a nested multi-grid version of our model, we are able to capture the pressure buildup and gas saturation accurately. And so you can see here the visualization, how the pressure buildup occurs over 30 years, as well as the gas saturation. And so I'll tell you in a minute what the FNO model we use stands for. It stands for Fourier Neural Operator, and it's able to accurately capture this multi-phase flow system for carbon capture and storage, as well as what we saw for weather forecasting in the previous slides. So we're also able to use the Fourier Neural Operator to capture turbulent wind conditions, such as in airflows, and ultimately be able to design flow-informed drones, that can function in highly turbulent conditions, such as around buildings. And this is indeed nature-inspired because, fish and other biological beings are able to have flow detection through the sensors in their body and very quickly and be agile in being able to overcome turbulent conditions. And so you can see here, this is a setup we have at Caltech where we are measuring the turbulent conditions in water. And using that experimental data, we are directly learning an AI-based model, the Fourier Neural Operator, and it's able to predict the flow in real time. And so this allows us to now design flow-informed drones and other navigation systems. And there are many other applications for Fourier Neural Operator. We're able to do multi-scale predictions of stress in materials, how the material is deforming and changing due to stress, or seismic tomography, predicting the source of earthquakes, or computational lithography. What is the ability to accurately model simulations at very fine resolutions at any tile size, and ultimately do mask optimization. So be able to capture the molecular dynamics of the coronavirus, especially how the conformational changes occur during its replication inside the cell. And you can see a short visualization of that here. So the idea is we want to be able to couple these kind of digital twins and other AI models together. And that's the promise. By being able to accelerate every stage of simulation, and in multiphysics, multiple systems coupled together, we can greatly accelerate and be ultimately able to plan and make better decisions. As an example here, if we want to plan for better renewable energy production and also understand its ability further into future, right? So as the climate is changing, how do the wind conditions change? So we have a climate model drive a weather model. And given the modeling of the wind, how much of the energy is being produced and how do we use it to plan the electric grid? We can all couple them together and plan this end to end. So let us now see our AI-based model, the Fourier Neural Operator, how it is very effective in capturing these different scientific processes, and why that is very compelling in terms of being able to get these enormous speed ups while being accurate. And why not just standard previous neural network architectures? Why do we need this new framework of neural operators? So for that, the idea of what these neural operators do is extend the concept of neural networks from finite dimensions to infinite dimensions. So the outcome is, if you think of a standard neural network, if it's trained on one resolution, let's say this coarse resolution here, we don't expect it to work well on the finer resolution. In fact, many standard neural networks cannot even incorporate inputs at a different resolution than what it's trained on. On the other hand, if we look at standard numerical solvers, let's say for partial differential equations, it is able to give you answers at any point in the domain. So we can have it incorporate different kinds of grids, different shapes of grids, different resolutions. So we want the same ability for also any AI-based model that is able to simulate different scenarios. So meaning that this neural operator learns operators that maps between function spaces. And hence, it is able to have query at any point in the domain, in a continuous domain, without the need for retraining. Meaning you can train in one resolution and directly test it at a different resolution without a huge degradation in performance. And so we define this as discretization invariance of neural operator, meaning we can query at any point in the domain. And not just that, once the model is trained, you don't retrain it again for different resolutions. And a trained neural operator can work at different resolutions, ultimately in the limit converge, meaning as you refine the mesh and ask for the neural operator for solutions on this changing mesh, you also have a convergence of solution, which is what is desirable. We ultimately want to be able to predict the underlying continuous solution, right? The underlying operator. And that is something that we guarantee with the design of neural operators. Whereas a standard neural network doesn't have any of this. And so the way we went about doing this is to use the framework of convolution with nonlinearity. But we want a convolution that can work at different resolutions, at different discretizations. And the way we went about doing this is through Fourier Neural Operator, where we solve convolution in the Fourier domain. And we can do Fourier transform at different resolutions and different grids. And due to that property, we have this being discretization invariant. And also because ultimately it converges to the continuous convolution. So you can see here, for instance, training it in the coarse resolution on Navier-Stokes, the fluid flow equations, and directly being able to evaluate it at a higher resolution. So there's no retraining. So we only trained it at this coarser resolution, and it's able to give you accurate answers at a final resolution. And we use this framework to accelerate a range of scientific domains that I showed you. The weather forecasting framework, carbon capture and storage, stress prediction in materials, computational lithography, all those were enabled by Fourier Neural Operator. Let me now show you a few other frameworks where AI is also able to make a huge impact, especially for chemistry. So this was a Gordon Bell Special Prize finalist last year. And what you see here is the ability to simulate at an unprecedented billion atom framework. And what we're doing is to understand how the spike proteins in coronavirus interact with the respiratory aerosol. So the dots here in yellow interact with the spike proteins in blue. And we want to understand what is the binding energy, because that determines the infectious nature of coronavirus. And so in order to compute this binding energy, we used an AI framework called OrbNet. And that is able to give you quantum level predictions while being 1,000 times faster than standard DFT calculations. And it's also useful for discovering new drugs, predicting the property of drug-like molecules, and being much faster than standard methods. We also are designing new drugs with better properties. It's a multi-objective design function in order to be able to discover new drugs. And what we've done is come up with a new framework that uses retrieval-based framework along with pre-trained generative model. And so with this, there's the flexibility of giving different databases of drugs with different properties as well as different task requirements in terms of properties, and being able to do this as a few short learning. And with this, we're able to improve upon existing drugs, such as for coronavirus. And you can see with better contacts, it is predicted to be a better drug than the original one. And so this retrieval-based framework gives you a flexible way of discovering new drugs while fusing information with pre-trained models. We are also looking at multimodal foundation models, such as those that incorporate molecular information along with text information. So you can give instructions for different properties and ask it to edit existing molecules. You can also see that here, if you ask a molecule to edit the molecule to be more penicillin-like, you end up with a molecule that does look more like it. So we can do all kinds of these natural language-based instructions for editing molecules and discovering new drugs. So in conclusion, I hope I gave you an overview of how AI is revolutionizing the scientific domains and very much integrating in scientific workflows. And we are able to see enormous speed ups from tens of thousands to even hundreds of thousands of times speed up in many of these scientific applications. And I think that's an exciting future. Thank you so much.